Okay, let's get started. Really loud today. I just had I want to take a survey of how you guys are doing on the homeworks. I know we haven't got them graded yet. We had homework 1 is graded, homework 2 is coming along, homework 3 is going to be really quick. We're just getting the last touches on homework 1 before we release it. How many people had a lot of trouble with homework 2? I'm just curious. Not too many. Okay. How about homework 3? Have you guys been having trouble with homework 3? It doesn't look like it. We've had a lot of complaints from the online course that these homeworks are really hard and they're having trouble with them, and I'm just trying to figure out if that's, what's going on in their side of the thing. They don't get the lectures. I mean, they can watch the lectures, but they have a different, completely different thing that they basically watch, different set of videos. I wanted to go through homework 2 and 3, though, and just run through them really quick. 2 especially, it didn't illustrate quite what we wanted, so I want to talk about some techniques we could have used to take a look at the data a little bit better. One thing about all of these homeworks is that this is an applied class. So sometimes we're going to give you instructions that are vague, it's not always intentional that they're vague, but sometimes they are. Things that'll make you think about how you're going to do it, roadblocks you'll run into that you either have to sort of look up online or in Piazza. That's an intentional thing to some extent. Sometimes it's just we've made a mistake. Lots of times it's because we want you to be working through and thinking of these. These aren't just problems you look in the book and write down and solve. Applied ML can be difficult, and practicing it and hitting your head against the wall is part of how you learn applied ML. So that's going to happen in the homeworks. Now, having said that, you shouldn't be spending 25 hours on a homework, which some people claim they have. You should be spending, a couple hours each week, maybe 3 or 4 generally on the homeworks. The first homeworks were a little bigger. They're a little harder. But 3 should be fairly straightforward, or should have been. I guess it turned it in yesterday if you did it. 4 should be fairly straightforward. And so these things shouldn't be taking you, 10 hours. Having said that, let's go through homework 2 real quickly. I put it together this is a Colab, but it's just a Python notebook. You can use a Jupyter notebook if you got local kernels. You can obviously run it through just the command line if you want, although you can't get nice pictures then, which is kind of a problem. So we got some includes. We downloaded the data. We loaded the data. I happened to use pandas to load the data. That was probably silly given how difficult it is to work with pandas sometimes. The first thing that you should be doing whenever you're looking at a data set is you should be looking at the data itself. So you just print out the data here in Python. You'll see if things look like they're making sense. So the first thing you see out of this particular data set is that the scaling on the features is all over the place. There's a bunch of 0 features, which seems a little odd. There's that first column, which the features are way too big. And then there's the last column, which is the label. And you'll notice that for whatever reason, when I imported this, it kept a space in front of it. When I print this out in pandas, it doesn't put the quotes around. And so I hit my head against this for about 10 minutes before I figured out that there was a space in front of that particular label. Anyway, so first thing you'll do in data sets is look at them. Next thing you do is generally you're going to look at the means and the sometimes the variances, but you'll generally look at the means. This is just another dump of the data set. Nothing special there. One thing you often want to look at is the label skew if you're doing supervised learning. In this case, the data was actually pretty skewed towards the negatives. I think I actually flipped the negative and positive here just when I labeled them. So these are actually, 75% was the negatives. So that's right. Okay, so that's a heavy skew. It's not as bad as it could be, but it does mean that your baseline worst case accuracy should be 76%. If you go below that, you could just call everything negative, and you would get at least 76%. So it's good to know where your baseline is, like where you cannot go below. Then it's good to look at the means, standard deviations sometimes, although those are highly scaled, so it's really hard to know what they mean. But you'll see the means, again, they're all over the place. You notice that the data, we know that the data isn't all zeros because all the means are non-zero, but there's this first one that is way too big. You don't always need to whiten your data or move it to zero mean and one variance, but you often will want to in situations like this. I went through and I rescaled the training set and the test set just to be, I actually did standard deviation of 1 and a zero mean. If you don't do that, you would not be able to learn. These numbers are just too big. I wrote my SVM code. It's hidden just in case you guys tried to steal it. Then what I did is I did a bunch of the graphs that we were supposed to do. So the first thing we did is I didn't try to tune lambda at all. That would have been an outside loop that I could have done. But I wanted to tune eta because that was the one where we gave you some graphs that we were supposed to look at and choose an eta learning rate. And the first thing we see is I tried a bunch of different etas. And this graph is really uninformative. That's a frustration that I'm sure all of you probably ran into. It's impossible to tell from this graph which eta is better. So that's a frustration. So the first thing that you often will do is take a running average. If you can't really tell, there's too much noise in your graph, you can take a running average. Most Pandas has a nice rolling average thing, but there's a bunch of different utilities. In sklearn you have one. In R there's things that'll do a running average. But when you take a running average of this data set, you see that there's a lot of variability, but you'll see that there is definitely curves here that are making a little more sense. Some of the etas are better than others. Some of them aren't learning as well. It looks like the eta of 0.01 works out pretty well, probably the best. Interestingly, the eta of 0.01 actually started pretty low, and it took a while to catch up, but it does actually catch up to be the higher, equal to the other eta. The other thing you can do if you see a lot of noise is you can increase your validation set size. I'm not quite sure why we set a validation set size that was 50. That's pretty low, especially when we have lots and lots of data. So if you didn't have a lot of data, you'd want to do some sort of cross-validation on your validation set to get a mean and a variance that would kind of show you where these values are. But given that we had a lot of data, we should just use it. Now things are still going to be noisy. We're doing random sets of data. You're going to have a little noise in there. But at least now you can see that some of the things are obviously above other ones. And that's going to get you in the ballpark of what you need to do. You can see that green is totally basically isn't learning anything. You can see that red is up at the top. I mean, exactly what we saw in the moving average before. This is the same thing, but I just took the moving average. Now you can see that the red and the purple are definitely up there. The green basically is not learning. The eta is just too small. It's taking too small of steps. And the blue is learning some, but it doesn't really get all the way up to the top. Now, often when you have a data set and there's a trend like the blue is showing, you need to run more steps, run more seasons, because you don't know if that blue is going to get higher and higher. So that's something that's important to do. If you get a graph like this where a line is on an upward trajectory, that's a thing that you need to investigate. So that's exactly what we did. We did 100 seasons instead of 50 seasons. Again, this is the really noisy graph. And here is the slightly more, that one's a little bumpier than it was. But you can see that the blue has come up. It may not get all the way up to the top, but it at least has come up, and you can see a little bit more that the blue maybe isn't a bad learning rate. The red and purple are still beating it, although there's a lot of noise in these. It turns out that this is a very noisy data set. It's very difficult. We dropped a lot of features because we didn't use the discrete features, and so it's a fairly difficult data set. And there's just a lot of noise in this data set. And then the last thing I tried was actually changing the eta like we suggested, where we started at a pretty high eta and then lowered it over time. And you can see that all of these started with what was the best eta before, the 0.01, and then they ended at various places. So I just did a linear interpolation. I didn't calculate M and N, but this is exactly what M and N would give you if you were doing this. The one takeaway from this is you really didn't notice much by reducing the learning rate. Sometimes reducing the learning rate will give you a big boost near the end of the learning curve. This data set is just very hard, so we never could get past this sort of 80 to 81%. Now, some people got 82, 83%. You could start in different places. You could use different validation sets. There's various reasons why you might do that, why you might get a better value. You might have used a little less noisy validation set because you didn't randomize it, and that might help. You might have used bigger batch sizes. That might have helped. So there's a bunch of variables that you want to look at. But the takeaway here is you really want to explore these things. And often if you're having problems, try to reduce the noise in the data somehow. Remove randomness if you can. There's a bunch of random processes here in the test set. The validation sets that we chose were a random thing each time. The order that we actually went through the data was different for each of the runs, and that makes actually a pretty big difference. If you get some bad data points just by chance early on, you can get moved into a pretty bad space, and it takes a little time to get back to where you would. So often you'll want to do your data points in a serial fashion instead of a random fashion. So there's various things you could try, and that's really the takeaway from this. Yeah, this is just the same thing. I did do a validation set where I did a really high, really large validation set. And again, you'll still see the noise. This was with the same, starting at the good eta, going down to a sort of bad eta or lower eta. And then the smooth values. You can see with 10,000 and a running average, you actually get a pretty smooth curve, which is pretty much what we like. And you can see more of, basically what you're seeing here is that it probably doesn't matter what the end learning rate is. So that's pretty much what I put together for that. Any questions on that? Okay. So hopefully, I mean, this is homework 2. You already turned it in. If you had trouble with it and you want to redo it, you do get after we come up with the grades, you get 5 days to resubmit if you want. You do get the 30% penalty, but if you really screwed it up for some reason and you got 20% on the homework, it's often worth doing it again. And it'll still be an improvement probably over the first grade. Now we're pretty liberal on our grading because we know this is hard stuff. So we really look for the things we ask for, and we don't worry about accuracies. If you guys couldn't learn for some reason, a lot of people got that 75% and really never learned. That we didn't dock you for in general. Unless you had problems with your code. If your code was wrong, then we're going to dock you. So homework 3, I wanted to walk through also. I did have some people who said that this was a really hard homework. Homework 3 should not have been a hard homework. You just had to follow the steps. And I think we even let you use a PCA library, so you didn't even have to follow the steps. You just had to use the PCA library correctly and calculate your errors correctly. So hopefully this was not I mean, some people were complaining of 25 hours on this homework, and it seems like there's something wrong if it took that long. But I just want to demonstrate that you can use sort of the same process. I loaded up data set 1 and the original non-noise data set. Again, first thing you do is you kind of look at the data, make sure it is what you think it is. I looked at just the first 2 data points. You can see that the data is, kind of close to each other. That's what we'd expect. Then I wrote down the procedure we're going to use. If you used a PCA library, you got to make sure you understand how that library is working. That's sometimes difficult because you don't really know what the right answers are. But it's important that you do that you kind of understand how that library is working. But for us, we're going to do exactly what we did in class. We're going to reduce it to zero mean. We're going to calculate the covariance. We're going to use the covariance to calculate the eigenvectors. We're going to rotate into that new space. We're going to project down some elements, and then we're going to rotate back and move it back, translate it back to where the mean was. So first things first, we just calculated what our error was on the original data set before we touched it. Then we calculated the means. You would expect the means of these things to be really close because the original data set and this data 1 is just a noised version. So if those means were really off by a lot, your PCA probably won't work. Because there's probably too much noise to overcome. I mean, PCA isn't magic. It uses correlations in the data to, recreate sort of the original data set. But if you have huge mean differences, you're going to run into problems. Then we just translated to zero mean. I'm not sure why I did the iris one here. We didn't need it. But I took the data 1 to zero mean. So these should all be near 0, bouncing between negatives and positives. We'd expect that. We calculated the covariance matrix. We expect positives along the diagonal. You always have the variance along the diagonal. Variance can't be negative. But you can have negative covariances on the other things. So you can see some of these things are anti-correlated. Some of them are correlated. It's hard to say with covariances. They're not correlations, so they're not scaled 0 to 1, or sorry, negative 1 to 1. Then we calculated the eigenvectors. We calculated this just using the eigenvector library. So literally, there is a library, NP linear algebra eigenvalues, that spit that out. Now, if you use PCA, it all did it for you. Under the covers, it did this, or used SVD to do it, but it's going to give you back the same thing. Then we rotated it by doing the eigenvector transpose. We rotated into the new space. we project it down, and that's incorrect. I don't know what happened there. Did we not project that yet? Just to show you a projection. There you go. There's a projection. I was debugging earlier. Then you can you rotate it back, add the mean in. Wait a second. Did I do it? And then we can calculate the new error, which should be lower than the original error if we've reduced noise. So the original error was 1.15 something. This error is 0.75. So that's kind of the breakdown of homework 3. Now that whole process could have been replaced by a PCA library. And I assume most of you did the PCA library because it's so much easier. The problem with the PCA library is you have to read the documentation and get it right. If you use it incorrectly, it's going to give you crazy stuff. Anyways, is there questions on that? Like I said, most of you have turned this in already. If you didn't, I don't think this actually helps you that much. It just shows that it works. Okay. All right. Let's go on to, we're going to do clustering today. We did multi-dimensional scaling and canonical correlation analysis, I think it was, CCA, last week. So today we're going to move on to clustering. It's a new chapter. So clustering is the process of, it's an unsupervised process, meaning that you don't have labels. If you're supervised, you have some labels that you're using. If you're unsupervised, you don't have labels. But sometimes you want to do things with your data, get some information out of your data, even though you don't have labels. Clustering is just grouping of data points. That's all it is. You go through and you try to group things that are similar. Now there's a couple ways you can do this, just sort of as broad categories. There's agglomerative, which means that you start with all the data points separately, and then you slowly glue together the ones that are closest. So basically, you'll start with, if we demonstrate this, we would have some points, and let's put some close ones together, and then we would group these first, and then maybe, these are hard to see, maybe group those two, maybe group those two, and then probably these two clusters are close, so we group those two together. These two seem to be pretty close. Oh! That's too bad, because I've got great art there. Okay, we'll start that again. Now we got to do this. Okay, let's just say that's it. Okay, so we might start with, let's put another one in there. We might start with this sort of group. We combine those two together. We'd start with, whatever, 10 or so clusters, however, one data point per cluster. Then we group the closest ones. So we group those two, we group those two, we come along, we group those two, then we probably end up grouping these two clusters together, then maybe these two clusters, and then maybe this guy gets grouped in, and then you get everything. So agglomerative clustering is just combining stuff and making it bigger and bigger. There's a couple different ways, or one real sort of important thing about how you calculate the distance between clusters when it comes to agglomerative clustering. So there's 3 ways to calculate the distance. There's one called single link. And single link basically groups it by the closest points in the cluster. So if we have 2 clusters, the distance would be measured between this point and this point. So that's single link. It's the closest two points in a cluster. Then there is complete link. And this is the more, complete link's the, always struck me as a weird one. Complete link is the farthest points. So this is the nearest. This is the farthest. So farthest point just means you have two clusters. You would measure the distance like this. That would be the distance between the two clusters. Then you just have group average. This is the obvious one that most people use. If you have your two clusters, the distance would be, the halfway point and the halfway point between those two guys. And that's the most obvious one that everybody pretty much uses. Interestingly, you can get into some very weird clustering patterns depending on what you use. If you use single link, you can end up with, you might connect these two, and then you might add this one in, and you might add this one in, and you might add this one in, and this one, and then this one, and this one. And so you can actually get these clusters that sort of follow a line through the data. And generally a cluster like that you don't want. You're really trying to group stuff into sort of, these blobs of data that are kind of similar to each other. You don't want things that, kind of fish around. So some of these distance measures are a little wacky on what they can come up with. So one thing we need to look at is, there's going to be a lot of pictures today, so I'll be flipping back and forth, so you guys are going to miss all my art. So this is called a dendrogram. The one on the right is called a dendrogram. And this basically shows how the clusters were built. Now, you can either be combining clusters if you read it from the bottom, or you can be splitting clusters if you read it from the top. And we're going to talk about splitting clusters in a second. But from the bottom, basically you have 6 clustered points. These guys represent these points. And then you can see the order at which we clustered things. So we clustered first 1 and 2, then we clustered 1, 2, and 3, then we clustered 4 and 5, then we clustered 4, 5, 6, and then we clustered these two big clusters together. And that's just, at each level you go up, you can see which one clustered. Then one of the things you can do with a dendrogram is if you look at it for, sometimes you have too many points to really visualize things, but you can often look at these and then sort of choose the number of clusters you're interested in by sort of selecting how high into the graph you go. So if I select down here, I'm going to have 6 clusters because it's going to be in each individual point. If I select right here, I'm going to have 2 clusters. If I select, I'm not sure why we don't have a line right here because this is informative. If we select right here, we'd have 3 clusters. And so when you're looking at this stuff, you can kind of see what makes sense, how can we cluster things, how is the data laid out. Another example of that, and I don't remember what this this data set is. It's a seed data set of some sort, but this is all the points in the data set and the dendrogram for those the clustering algorithm. So if we look at this, we actually see that there's some major clusters. Kind of if we cut it at this point, we would see that there's kind of this major cluster, And then when you get over to this side, you got some oddities where you have maybe these subclusters. You have sort of these almost orphaned points over on this side that are going to form a really small cluster if you cut it kind of right here. You'll often get orphaned points, like if you cut it right here, you'd get a nice cluster out of this branch, but this branch would be this really small cluster. This is one of the problems with agglomerative clustering, is that you end up with some good big clusters, and then you end up with a bunch of sort of trash that just didn't fit anywhere, was far away from everything, and depending on where you cut it, there's just no way to get nice, evenly sized clusters. That for all clustering algorithms, that's going to be a problem, but it's especially a problem with this sort of agglomerative approach. Now, the opposite of agglomerative approach is, I can never say this, divisive, where we cut things in half. So what you do is you start with a single cluster, and you just, at each point, you sort of choose a split point, and you split it in half, and you repeat. So if you look at the dendrogram, it would look exactly the same. It's just we'd start at the top, and we'd move downwards. So we'd first start with a single cluster sort of up here, then we split it in two, then we split it in two again, then we split it in two over here, and we just keep splitting it. We don't often use this kind of clustering. There are some applications where it makes a lot of sense, but there are often very specific applications where it's obvious that this kind of clustering, where there's these obvious split points where things should be split. You often aren't going to split on sort of distance metrics. You're going to split based on sort of an application-specific sort of cut points. A lot of image processing will do that, where you'll kind of take things and find edges and split to cut an image up into sort of clusters of the pieces of the image. And it's a very, you start with the full image, then you cut along some lines, then you cut it some more, and you cut it some more, and you end up with a bunch of pieces of the image. It's common to do that for some applications. It's not very popular for most applications. So those are kind of the high overview of sort of some common techniques. Now we're going to talk about a very specific technique, which doesn't actually fall under either sort of those two categories, oddly enough. So we're going to talk about something called k-means, and hopefully you guys have heard of k-means. It's a pretty common algorithm. Oh, good point. We should definitely do that. There we go. Okay, so k-means. K-means is a little hard to draw, but basically what we're going to do is, if we have some data points, we're going to start by having some clusters. Now it doesn't really matter what these clusters are initially, so we're going to find a cluster, and then let's call this a cluster. And then what you're going to do is, iteratively, we're going to calculate a center point for this cluster. So this one is going to be something like this. This one is going to be something like this. And my picture was really poor because it's not going to really illustrate this. But what you would do then is you would look at each point to the centers, and you'd reassign the clusters based on that. So you'd always assign to the nearest cluster center. And then you have everything at a cluster center. You would recalculate the cluster centers, and then you'd do it again. You'd reassign everything, recalculate the cluster centers, reassign everything. So that's kind of the system that you think about k-means. One of the downsides of k-means is that you have to select k a priori. Like we'll talk a little bit about selecting k in a second, but k needs to be fixed in order to run this algorithm. So unlike like agglomerative, where you can sort of run it and you don't have to choose the clusters up front, the size, the number of clusters up front, k-means you have to say, I'm going to run this for 10 clusters. I'm going to run this for 2 clusters. So that's one of the downsides of this. So just to talk about how you would formally generate these clusters, we have to look at an algorithm. So we're going to just define a delta. And a delta is going to be, the I is going to be the data point, and the J is going to be the cluster. That is a terrible arrow. And then the value is 1 if the data point is in cluster J and 0 otherwise. So this is just an indicator function that basically says, which cluster am I in? So there's a couple things. We want all of the points to have a single cluster, and we want every point to be in a cluster. So for every point to be in a cluster, we need delta ij. Let's see what the should be. If you it's for all I. If you run through the j's, all the j's, you should only be in a single cluster. And that's just the fancy way to do it. And then for the other way to do it is, the other thing to do is to say, that every cluster needs to have at least one data point. So if you run through all the clusters, again, this is iterated over I. For all j, you need to have at least one point in a cluster. So you can't have empty clusters. Empty clusters basically are meaningless, and something probably went wrong. So given these definitions, we can write a formula which is basically a cost formula. Delta is the assignments, C are the cluster centers, and then what we want to solve is delta ij times the distance between the data point and the cluster, and we're going to square that. So this is really the cost function of having a layout of a certain delta j's with certain cluster centers. Now, if we were going to find the optimal clusters, we'd want to minimize this. We'd want to find the cost that is minimized with the constraints that we specified right up here. We'd minimize that, but we'd constrain it according to this so that we couldn't have things in multiple clusters and we couldn't have empty clusters. Now, the problem with this is doing any minimization on this function is going to be really difficult. And the reason it's really difficult is that this is an integer. It's either 0 or 1. And doing optimization with formula with discrete values is very difficult. So we're never going to be able to do the optimization that, sort of the minimization that's going to give us the perfect clusters. So this is why we go back to the algorithm I was a little bit describing earlier, where it's an approximate clustering algorithm. It's not going to give you the best set of clusters, but it will, in general, in practice, give you a good set of clusters. It can go off the rails sometimes, whereas if we could minimize the actual cost function, it would always give us the right answer. The sort of heuristic we're going to use can break, but it's still pretty good. So really what we need to know is if we know the points in the cluster, then we know the cluster center. And if we know the cluster centers, then we know where each point needs to go, because we can just put it in the nearest cluster. This just comes up with the algorithm. So we will start with random cluster centers. And I'm going to put random in quotes there, because we're always going to start with data points. We're going to randomly select k data points. So they're not really, they're random in the sense that we're going to select different ones, but do you have a question? Do you also make sure that you select them without replacement? Yeah, you do it without replacement, because you don't want you obviously want the cluster centers to be different. So you do it without replacement. Now your data sets are going to be really big compared to your K, so that's not really, it won't be an issue doing without replacement. And the reason you use data points is just because you want to get it in these cluster centers kind of in the ballpark. If you just used a bunch of random numbers, who knows where those would be compared to the data points. And if they're not sort of in the domain of the data, your clustering algorithm is going to just go off the rails. I'm kind of drunk today on there we go. Okay. Then you do, given that, you would assign each point to nearest cluster. Recalculate. Recalculate centers. And then fix empty clusters. And then you would repeat. So you would, this is exactly what I described when I was drawing the picture. You assign the points to a cluster, you recalculate the cluster centers, you then assign the points again, you recalculate. The only oddity there is that we want to fix the empty clusters. If after you assign all the points, you have a cluster that has nothing in it, remember we said all clusters have to have something in it, we would want to choose a new random point and create sort of a new cluster from a random point. Now you typically would want to choose that semi-intelligently, so you might choose a point that's fairly far from its cluster center. So maybe the farthest point out from a cluster center, you would choose that, or find the 10 farthest points and select one of them randomly, just to add a little stochastic process in there. But that's the basic algorithm. This algorithm works extremely well. It's kind of amazing how well it works. K-means is used, even if you use other clustering algorithms, more complicated clustering algorithms, some of them which we're going to talk about in probably Thursday, those more complicated clustering algorithms almost always start with K-means. And you do just a couple iterations of K-means to get the clusters kind of maybe in the right spot, and then you'll use a more formal technique to make sure the clusters are exactly the way that they should be according to the formal technique that you're using. So k-means is definitely a common algorithm that you almost always use. All right, let's look at, let's see what figure. According to this, I'm supposed to go to figure 12.5. That doesn't sound right. I think more likely I wanted to show these ones. So this is our flower data set that we did PCA on, actually. And you can see there's actually 3 categories in this data set. And we're going to look at a couple different clusters that can come out of this data set. So you cluster like this, and this is pretty obvious, a pretty obvious clustering of these 2 things. Now we know actually there's 3 labels on this data set. A lot of times when you're clustering, you don't know that, so it's you couldn't say that that was the right number. It actually looks like these are pretty good clusters from this perspective. If just look at 3 clusters, same thing. We start seeing that there actually is some additional structure to this, maybe. If we go to 4 clusters, now it's starting to kind of, all the clusters are sort of starting to blend together. It's hard to say whether they should be split apart. I don't know if we go to another cluster. So one of the big questions of k-means is how many, what k should be. How many clusters should you be using? Now you can't simply say I'm going to increase the clusters k until I have 0 error. Because if you're really aiming for 0 error, you could just increase k to be the number of data points, put each data point into a single cluster, your error would be 0. And so you can't just say, I want to get 0 error on my data set. So that doesn't work. Now what you can do is you can run clustering with a number of different k's and then add some sort of penalty as the k's go up. So that'll push the number of clusters down, whereas the arrow will kind of try to push the k up, and it'll find some happy medium. Now, of course, that requires some hyperparameter where you need to know this penalty on k. If that penalty is too low, you're going to get a really high k. If the penalty is too high, you're going to have a really low k. It's not the best. The second thing you can do is just try a bunch of k's. And then most of the time you're using clustering for some application. And that application might have some guidance as to whether the clusters are good or bad. For example, we looked at the projections here, and we probably could tell which clusters were good or bad just by looking at sort of the projections. But you could, depending on your application, if you're doing image work, you might be able to look and say, oh, this many clusters of different colors is the right thing to do. And it'll be sort of obvious looking at the image. So that is a very heuristic. It's not there's no formalism there. But it's actually used quite a bit. People sort of just choose k a lot of times and go, maybe I'll move it up a little, maybe I'll move it down, see what happens. The last one is a little more systematic. You can look at the errors, the number of errors, sort of the distance to the cluster centers versus the number of clusters. And you can plot that. And so that's what we plotted here. And what you'll often see is there's sort of this this bend in that, that cost function. If I were to read this, I would probably say, you know, it came down and then the bend is right here around 4. And so I'd probably say I'm going to use a K of 4 in that case. Now, we happen to know this data set has 3 labels, so a K of 4 is too high. It's not perfect, but it at least tells you kind of like, you know, the differences between clusters start getting really small down this way. So that's kind of probably how we choose K. There's one thing to point out. You'll actually see that the error went up right there. That's because we're using a heuristic again, and it's going to depend on where we start, and where we end up is going to depend on where we start, what our initial clusters were. So you can actually get, you know, sort of a little variance in the error here, just due to the fact that we started at a different place, we got different clusters. It's an approximate algorithm. It's not finding the exact best minimum answer. So you'll get noise like that. One aspect of k-means is that we talked about, and that is kind of a limitation, is that we are forced to assign each data point to a single cluster.
I was wondering if k-means has like a theoretical worst case to it, or like if it actually is provably like can be proven to reduce the cluster well on even the worst case.
I don't know of any theoretical proof that it's going to cluster well, depending on the, you know, what the data set is. In practice, it does. Again, we're using a heuristic, so there's probably degenerate cases where that heuristic leads us to a bad spot. Definitely, when you're using a heuristic, generally the sort of the theory that would give us a minimum isn't going to be there. But even if you use the exact cost function, I can't actually say that I've heard of sort of a minimum, these clusters are good. A lot of times clusters depend on your application, so what you call a good cluster or a bad cluster is, you know, up in the air. All k-means, even in the formal definition, all it's guaranteeing is that it assigns the cluster according to that cost function. But of course, then we're using a heuristic that doesn't do that. But it should be close. So the answer is no, I guess. Not that I know of. So one problem with k-means is we'll often have a situation like this, where we have a nice little cluster, and then we have some point right there. No, you can't. This should automatically switch back and forth. It'd make my life a lot easier. So it's pretty obvious this is your cluster and this is your cluster, if you have a K of 2. The question is, where does this point go? Now, if we calculate the distance, it's going to be closer to one cluster or the other. But arguably, this point could be in this cluster or in this cluster. And if you include it in either one, it's going to skew that cluster center sum. So if you include it in this one, all of a sudden the cluster center is going to move this way. If you include it in this one, the cluster center will move that way. And that may not be what you want. So we'll often relax the requirement that a point is only in a single cluster, at least for the purposes of calculating the clusters. Now, in the end, you generally want to know where the closest cluster is, and you'll end up putting a point in a specific cluster. But while we're calculating clusters, we can use what's called soft assignment. So soft assignment we're going to replace are delta ij with weight ij. And each weight ij, let's see, that's the weights are all going to be greater than or equal to 0, and the weights across all clusters for a given data point are going to add up to 1. So basically, you're going to get partial assignment. You're going to take any given data point and put it partially in multiple clusters. And again, this is just for the calculation of the clusters. Once you're done and have calculated the clusters, you'll probably want to know that this cluster or this data point goes specifically into this cluster. You might get some information by saying, this one's partially here, partially there, but generally you want them in a specific one. Now, the cost function, again, we don't use this, so probably doesn't matter that much, but the cost function just replaces the delta with this. Transpose, there's a bunch of i's and j's in here. It's a CJ. So all of a sudden, we're just gonna calculate the cost by taking sort of the weight of each of the distances for any given data point. Then we need to calculate cluster centers. So cluster center J is just going to be the weighted average this is over I, the weighted average of all of the data points, and then you got to normalize it by all the weight that went into there. So that's just a weighted average that just adds up all the data points for a given cluster, all the partial data points, and then normalizes it so that it adds up correctly. Now, of course, the question then is, how do we come up with the weights? A standard technique, now you could weight these things any way you wanted. You could come up with a bunch of different weight calculations. A pretty standard one is we're going to calculate an intermediate value. And this is going to be e to the negative second norm of the distance between the cluster and the data point. And then resized by a scaling factor of sigma squared. And then we're going to calculate ij equal to Sij over, let's see, this is L equals 1 to K of the SIL. So you just sort of calculate it according to the proportion of all the S's for a given data point. This works pretty good if you want to do that sort of thing, if you're looking for soft assignment. Again, it's not the only way to do this. We could come up with soft assignments in a lot of different ways. But this one works pretty well. There is a scaling factor in there that will control how soft your assignments will be. If sigma is very high, then your assignments become very equal. Like the higher it goes, the less you pay attention to the differences in the distances. The lower it goes, the more sort of hard the assignments become. If you go low enough, they're really you're back to basically the standard k-means. Now the math never works out that way because you'd have to go down to negative infinity, whatever. But ignoring that, you get more and more towards standard k-means at that point. Of course, this is a hyperparameter. There's no a priori way to choose it. You end up trying a bunch of them, looking at the clusters, seeing what happens. That's about the only way that you can do it. So questions so far? Hopefully this stuff's pretty straightforward. There isn't a lot of craziness that goes into k-means. K-means is a fairly expensive algorithm. So in the end, you want to put each data point into a cluster, but often you don't want to use all of the data to calculate the clusters. So one thing you can do is you can just subset the data when you calculate the clusters. And that works just fine. But you still have, if you have a high number of clusters that you want, you still have to have, for the number of data points times the number of cluster calculations that you need to do. So there's quite a few calculations if you have a high K. So there's something called hierarchical k-means. And what hierarchical k-means does is you just start by, let's say you have a bunch of data points. Right there, that one. Okay, so I got a bunch of data points. All I'm going to do is I'm going to do iterations of k-means where I sort of increase the k. So the first time I did k-means, now I got to wait till it converges for each of these steps, which means I'll do to come up with the clusters, I'll run the back and forth multiple times. But let's say I come up with this cluster and this cluster. Now what hierarchical k-means is going to do is you're going to take each of those two clusters and then you're going to split each of the clusters again, using only the data points within that cluster to calculate it. So for this one, we're going to double the number of clusters by finding this cluster and this cluster. And for this one, we're going to find this one and this one. And this is a pretty data or calculation efficient way to do clustering. You can increase the data that goes into these clusters each time. You can recalculate, you can add in more data if you need it. But you're always working with smaller data sets, which is a good thing. This actually becomes sort of a divisive sort of algorithm where we're splitting each time over and over. But it works pretty well. It gets different clusters than if you were to just say, I want 4 clusters versus I want a hierarchical of 2 and then split them again to 2. It's going to get different clusters. But those clusters should be about the same. K-means, our heuristic isn't exact anyways. You can get into some degenerate cases where you get some odd clusters with very few points in them. There's not much you can do about that. Okay. The next thing we need to talk about, using a lot of paper today, is using histograms for analysis. So sometimes you want to get some information about things where you use clusters to sort of see how things differ. So let's say I knew I had some labels, but I have a bunch of features that I want to look at, sort of how different things come out. I'm not giving a very good description of this. But what we can do is we can take our data, generate a bunch of clusters, and then we can look at the histograms of how those clusters, how often a given label falls into a cluster. So we might see something like this. So first thing we do is we cluster all of our data, ignoring whatever we want to split on. So let's say we got 2 histograms, and we have a feature, let's just say we have feature 1, and it has two settings, A and B. Now we cluster without looking at A and B, otherwise A and B would sort of jockey around all the center points. And then once we have those clusters, we look at all the data points that fall into a given cluster for the A set versus the B set. So we look at all of the N data points, and you're going to get a histogram. You know, if this is cluster 1, 2, 3, 4, you're going to get a histogram that's going to look like, I don't know, down. So let's say this is 1, 2, 3. So let's see, how many data points did I have there? I had 6. 1, 2, 3, 4, 5, 6. And I've just put them, I've just counted how many times label A or feature A fell into given clusters. And this gives us sort of an information about how A and B are going to differ. So maybe B is going to look something like, 1, 2, 3, 4, 5, 6. Maybe it looks like that. Now we can see that A and B are actually very different. Their data points fall into very different sets of clusters. And it kind of gives you a fingerprint that you can use for later on if you wanted to, say, classify A versus B. You could use these clusters to sort of generate a fingerprint where the labels for A would be, you know, just the histogram numbers. So it'd be, what, 3, 1, 0, 2, just the counts. And the sort of feature vector for this guy would be 0, 2, 4, 0. And that's going to let us sort of create a, like I said, a fingerprint for these different sort of classes. So let's look at an example of this. Okay. Let's see if I can zoom that a little bit. Okay, so this is a data set which shows kind of the consumption of different products. And I think it uses monetary value is how it rates stuff. But it basically is saying, you know, there's what they call two channels, where the channels are either it's a hotel/cafe sort of thing, or a consumer. So they sort of have a feature that says, is it a hotel that was buying these products, or is it a end product consumer, you know, a person who, you know, is just buying them for themselves. And then they have different locations across. I think this is from Japan, but I might be wrong about that. But I think it's there's 3 locations. So they have a feature that says this was in city A, city B, city C. And then they sort of plotted, you know, they figured out for each of those locations and either consumer or hotel, they figured out how much milk they're buying, how much, you know, frozen things they're buying, and things like that. So then what we did is we looked at clustering, k-means clustering, for all of these data points, where we ignored the channel, what they're calling hotel versus consumer is sort of the channel, and we ignore location. And then we looked at the clustering of all of the consumption. And what you see is, this is that knee plot where this is sort of your within group sum of squares, and the number of clusters. And I think we looked for the knee, and I can't remember exactly what we chose, but it's either, you know, the knee here is maybe, you know, 7, 10, somewhere in there. It probably doesn't really matter which one you choose. And then we did the histogram that I just talked about. So I guess we used 10 here. And we just counted up, you know, so this first one, For channel 1, which I think meant consumer, and region 1, which is one of the locations, the data fell, many times into this first cluster, sometimes into the second cluster, never into the third, sixth, seventh, eighth, ninth cluster, and then they fell into this. And then the same thing going across is regions, and up and down is basically consumers versus hotels. And what you see from this is, again, there's a fingerprint. And you're seeing that across regions, consumers pretty much buy the same thing. It doesn't matter where you live, an end consumer is buying sort of the same things. The patterns here are kind of the same. I mean, certainly this one and this one are very similar. This one, not so much. But these two, they're buying a lot of the same things. Down here, first of all, you see that the consumer pattern is very different from the hotel patterns. The things that hotels buy are extremely different than the things that consumers buy, at least in the ratio is sort of how much you buy of them. And then you see that kind of the channel 2, definitely these two are very similar. You could say that these two locations are buying sort of the same thing, but this region, for whatever reason, the hotels and cafes and whatever that got thrown into that channel are buying very different things. So that's how you sort of read these histograms and how you use them. And now if you wanted to, if you didn't have the labels of sort of channel and region, or if you wanted to make a model that, if you had those labels but then you wanted to build a model to categorize new data, you could use these histograms as sort of feature vectors. And you could build a classifier that would say, I think that this new data point, this new consumption pattern, goes into channel 1, region 1, or region 2, channel 2. And that's actually exactly what we're going to do next. I think the next thing is going to take a little time. So I'm going to let you guys go early unless you have questions. You're welcome to spend 2 minutes asking questions, but if not, I will see you guys on Thursday. What's up?
I have a question regarding the previous homework.
Yep.
I don't really get why in the last exercise, the last question where we had to do feature selection of 2 components, we had 4 components resulting. And when I tried using the PCA library from Sklearn,
Yeah.
and when you said components, it actually outputted 2 linear components.
I don't think there was any rhyme or reason as why you did that. Now remember, there's 2 ways to come up with the principal components. You can use the original data set, come up with the principal components, apply those to the noisy data set, and then push it back into the original space. That's one way to do it. But if you're trying to denoise something, you often won't have the original data set. It's very odd that you have both the original and the noisy one, because if you did, why would you do this? So often you'll have the principal components from the noisy data set. And if you use those principal components from the noisy data set and you used all the principal components, you would generate the same thing that you started with. Because you subtract the mean, you rotate it back the exact same way, you add the mean back, and actually, if you calculate the error and if you looked carefully at the original error between the iris and the noisy data set, and then you looked at the one that is the 4 principal components, it's the same error because you didn't change anything. So the only way to get rid of noise is to reduce the number of principal components. Now, if you base the principal components on the iris data set, you still have the same problem that you're going to rotate it and rotate it right back. So you always have to use less than, whatever the number of principal components is.
But my question was more on the dimensionality of the vectors than because in the sklearn methods they drop.
How many? I mean, we only have 4.
Yeah.
You can drop 1, 2, or 3, or 4.
Yeah, exactly. But when you compute PCA with 2 principal components, aren't you supposed to drop 2?
You project down 2 of them, and then which is exactly what I actually did.
Yeah, exactly.
And then you bring it back. Yeah, that's exactly what you do.
But on the output file, there were 4 components, right?
You're still. Oh, okay. I see what you're saying. Even once you drop the principal components, you still have our P is still going to be some, let's say A, B, 0, 0, right? Because we've dropped 2 of them, or we dropped 2 of them, we retained 2 of them. So when you rotate this back, you're still going to have 4 components. You don't drop this. You drop these in the rotated space, but in the original space, you're still going to have this. Remember, this is just a rotation. So a rotation, if there's 4 here, there's 4 in the space that you come from. So you start with 4, you rotate it, and then you go back to 4. So you don't end up dropping. The projection isn't in the original space. It's in the rotated space.
And this P vector corresponds to.
That's the projection vector. So if you looked at we start with the mean vector, the mean 0 vector. We rotate it into the new space. We project it down. We rotate it back and add in the mean. So this is the original. This is in the original space, but has lost these 2 components. But again, it's still a length 4 because we projected it down in here, but we didn't make it into a vector like this. We kept those.
Okay, and so for X, we can have non-zero entries.
Yes. Because if you look in this in 2D, if you have, let's say that was your eigenvector, this was your P. If we project it down, now we're down to here. But then if we rotate it back into some space, now we're back up to there, and we have 2 components that are going to be non-zero. Even though in the projected space here, it was, the y is 0.
Okay. And then in that case, why does sklearn just get rid of 2?
I don't know. I'm not sure why sklearn would do that.
Yeah.
It shouldn't be returning. It shouldn't be returning less. I would guess that there's something wrong with the way you're calling sklearn, or it's got to be a parameter because you should be getting back. You might be getting things in the rotated space, not in the original space. So that's the only thing I can think of is that you're actually getting the P, not the X hat back. So we're okay. We got a couple more minutes before we have to move.
Hi there. I'm trying to do the later. I already sent you an email.
Okay. What do you need though?
Later. I just need
An extension.
no extension. Like an email or
A late ad.
Yeah. Late ad.
Oh, sorry. And I didn't reply. Can you send me it again? It just got buried in my email.
Can you just run me a paper thing right now and I can.
Sure. Yeah, and you get 5 days technically from the day you add. And then you're not supposed to get any days from homework 2 and 3 and 4, but of course if you just added, it's weird. But yeah, you get 5 days for that first homework. If you're adding right now, you might have a problem. You know.
Because I added to the grade school like a couple days ago.
Yeah. Yeah, you shouldn't. It should be from the day you added to the course. You get 5 days, basically.
So the thing you guys are not handling that.
Well, when did you add to the course? You should look that up, and you get.
I did submit the homework.
Okay, yeah, you just need to look and see when you add it, and then let us know when you're going to get a grade and it's going to have a penalty, and then just ask for a regrade and say I added it this day. I should have been.
Homework one.
Yeah.
So you can't.
Oh, you're saying it's actually closed. It shouldn't be closed. It should still be open. I'll fix that. Yeah, that shouldn't be closed. You guys, even after we grade them, you can resubmit. So, yeah. Yeah. Oh. Thanks.